In Oersted's experiment, we have seen that a current carrying wire produces magnetic field around it. Now I am going to discuss the magnetic field due to current carrying a straight wire. Okay. First of all, watch the following video in which you will see the magnetic field lines produced by a current carrying straight wire. Okay. Now watch it.
I have a piece of plastic through which I've drilled a hole, and then I took a wire and looped it through the hole 10 times. So I have 10 strands of the wire here flowing through this hole. So if I have 1 amp of current flowing in the wire, I will have essentially 10 amps that's flowing in a straight line through the hole in the plastic. I'm now going to sprinkle some iron filings onto the plastic. I will now apply a current, and I will have to tap the plastic to get the iron filings to move. And you can see how the iron filings have rotated to form circles around the wire, indicating the form of the magnetic field intensity generated by a current carrying wire.
So in the video, we saw a current carrying a straight wire producing circular magnetic field. Okay, as shown in the diagram. In the diagram, we have a straight wire carrying current I. Okay, and this straight current producing circular magnetic field around it. Okay, and I have written certain points about this magnetic field. Okay, the first point is the magnetic field is in the form of concentric circles with the center at the wire. Okay, as you can see, these magnetic fields are in the form of concentric circles, means having common center. All circles have a common center which is lying at the wire. Okay, and the second point is the magnetic field lies in a plane perpendicular to the wire. It means these circular magnetic fields lie in a plane which is perpendicular to the wire or current. Okay, so this is the plane in which these magnetic field lines are lying. Okay, and this plane is perpendicular to the current. Okay, third point is the direction of magnetic field is given by right hand thumb rule. Okay, so this rule is very important, right hand thumb rule, because this rule gives you the direction of magnetic field produced by a straight wire. Okay, and according to this rule, if you imaginarily hold this wire by your right hand such that the thumb is pointing the direction of current. Okay, the thumb is pointing the direction of current, then the direction of magnetic field is given by the direction of curling of your remaining fingers. So my remaining fingers curling in this direction, it means the magnetic field lines would be in the direction of my curling of the finger. Okay, means anti-clockwise as seen from the above. Okay, so this is how we can define the magnetic field around a straight wire. Okay, note it down. Now come to the fourth point, that is the magnetic field strength denoted by B is directly proportional to the magnitude of current. Okay, mathematically we can write magnetic field strength is directly proportional to the current in the conductor. It means when we increase the current in the wire, the magnetic field strength increases, and when you place the magnetic compass, okay, near the wire, then the magnetic compass is strongly deflected, okay, by the current, because the higher the current, stronger the magnetic field produced, okay, and the magnetic needle will strongly deflected, okay. Note it down. The fifth point is the magnetic field strength is inversely proportional to the distance from the wire. The distance from the wire is denoted by small d, and mathematically we can write magnetic field strength B is inversely proportional to the distance from the wire, okay. So from this point we can say that when we move away from the wire, the magnetic field strength decreases, and we move towards the wire, then the magnetic field strength increases, okay. So note it down. And the SI unit of magnetic field strength is Tesla, okay. So Tesla is the SI unit of magnetic field strength.